Hello everyone, and welcome to the Computational Thinking in the Classroom, a virtual workshop for educators. My name is Adriana O'Brien, and I'm in the Partnerships and Educational Outreach for Wolfram Research. I've taught math at the high school and junior college level, and I've also led numerous programming workshops for elementary, middle, and high school. We only have an hour to get through a lot of material, so let's get started. Here's an overview of what we'll be covering. Before diving into the tools and activities, I wanted to briefly discuss computational thinking. At the end of the workshop, I'll highlight a few resources to help you get started. When I go to conferences, meet with teachers or administrators to discuss computational thinking, I always ask, what is computational thinking? What does it mean to you? You'd be surprised that the answers vary greatly. So before we delve into computational thinking, activities, and tools to support it, I wanted to make sure that we're all on the same page. I found a really nice quote from Jeanette Wing. Computational thinking involves solving problems, designing systems, and understanding human behavior by drawing on the concepts fundamental to computer science. It's important to note that it's not just programming, and it's not just problem solving. It's much more than that. Let's examine some characteristics of a computational thinking activity. Here I've listed a few characteristics from CSTA and ISTE. I'll go into that a little bit later, but I wanted to elaborate and to highlight a few characteristics that I think really highlight what a computational thinking activity is. It's formulating problems in a way that enables you to use a computer and other tools to help solve them, logically organizing and analyzing data, representing data through abstractions such as models and simulations, automating solutions through algebraic thinking, a series of ordered steps, identifying, analyzing, and implementing possible solutions with the goal of achieving the most efficient and effective combination of steps and resources, generalizing and transferring this problem-solving process to a wide variety of problems. Throughout these characteristics, you can see aspects of what a developer and a programmer might do, but it's applying them to a way of thinking and approaching real-world problems. When considering adopting a computational thinking approach, it requires a pedagogical shift from standard or traditional teaching methods. The International Society for Teachers in Education and the Computer Science Teachers Association collaborated to put together a wealth of materials dedicated to understanding and implementing a computational thinking approach. In addition to the standards produced by the ISTE and the CSTA, we also have a new set of standards from the AP organization called the Computer Science Principles. The information included in these standards, in these principles, in all of these resources sheds light on what it means to introduce computational thinking or to bring computational thinking into the classroom. But why are computational thinking skills so important? The New Jersey Institute of Technology put together a really nice infographic about computer science, which is the basic tool set for computational thinking. I really like this part of the infographic. It states that they predict by 2020 that there will be 1.4 computing jobs. We will have about 400,000 computer science students. That means we have a shortage of 1 million qualified applicants for all of these computing jobs. It is important to introduce computational thinking and programming skills into the classroom so that we can address the needs of the ever-demanding industry in technology, so we can meet the demands of technology industry. The next couple of slides elaborate what computational thinking entails. The first is looking at computational thinking via project-based learning. Now, project-based learning is not a novel idea. It's been around for quite a long time, and there are numerous educators that are proficient in adopting a project-based learning, which is not too far from computational activities. The George Lucas Educational Foundation put together a process for developing project-based learning, which can be incorporated into computational thinking. It says, start with an essential question. design a plan for the project, create a schedule, monitor the students and progress of the project, assess the outcome, and evaluate the experience. This is not too far from what you would expect the process to be when you take a look at computational thinking activities. They had a really nice quote about PBL. It states, "The question that will launch a project-based learning lesson must be one that will engage your students. It is greater than the task at hand. It is open-ended. It will pose a problem or situation that they can tackle, knowing that there is no one answer or solution." The point that the George Lucas Educational Foundation made is that structuring quality questions is extremely important. That's something that the computerbasedmath.org embraces fully. They have adopted computational thinking into curriculum development by focusing on these messy real-world questions that drive students to critically analyze and solve them. You can see how traditional curriculum compares with modules in the computer-based math curriculum. Instead of focusing on something like mean, median, and mode, they ask the question, am I normal? And through that question, the students will inevitably learn about mean, median, and mode, but it's the approach. It is the problem-solving aspect, that computational thinking that is inherent in asking these messy questions. Another module that they have, as opposed to a unit on probability, their question is, do I know what I do not know? For averages, range, and percentiles, you can replace that with, are girls better at math? Representing and selecting data now becomes, how can I convince you? And perhaps a unit on distribution fitting becomes, how tall is the tallest woman in Estonia? Like I said, by asking these messy questions, by focusing on real-world information, real-world problems, we are giving our students the opportunity to become better problem solvers and think computationally. Conrad Wolfram, the founder of computerbasedmath.org, has a really nice quote that I reference a lot, is that we want a first-rate problem solver, referring to students, not a third-rate computer. We want to give students the opportunity to learn how to become a problem solver, to think computationally. When you focus on messy questions, you're dealing with scenarios and problems that aren't easily computed by hand. You need computers to do the heavy lifting. This is most notable when you're dealing with real-world data. Some examples of bringing in real-world data into the classroom: financial stock information. There are a wide variety of open resources that house data that you can use at any time. The U.S. government, NASA. There's the ability to collect your own data. This presentation will be made available after the workshop, and I have some hyperlinks in here. And I have some hyperlinks in here that you can explore some more resources. But like one of them, collecting your own data, if you have a device that's connected to your computer, you can bring in all sorts of information. You can bring in all sorts of data. As I mentioned before, it's important to let computers do the heavy lifting so that students can be free to do the problem solving and analysis. A vital tool to support computational thinking in the classroom is the Wolfram Language. There's a wide variety of programming environments that you can get access to the Wolfram Language. The first and most notable is Mathematica. Mathematica and the Wolfram Language are free on the Raspberry Pi device. We also have a couple of online options. The Wolfram Programming Cloud, released last year, there's a free tier to get started. And then coming soon, we'll have the Wolfram Programming Lab, which is specifically geared towards K-12. One of the great features of the Wolfram language is the ability to code in natural English. It's an immense help for those just learning the language that aren't familiar with the proper syntax. For example, I can type in solve 2x plus 1 equals 5. No special particular syntax. All I did was type it in, and there we go. I have now coded in natural English. It gives me the proper syntax to help learn, to help guide me that if I wanted to do this again, if I wanted to use the proper syntax, here it is. More detailed requests can be made, but try to keep the language as simple and direct as possible. So this one instead is now producing a graphic of a plot. Again, it's giving me the proper syntax as a guide. Another great feature of working with the Wolfram language is that the programming environment, either Mathematica or Wolfram Programming Cloud, it's a document-style interface. What I'm showing you right now is of itself a programming environment. I could start programming right now. I'm in Mathematica. This is just a presentation mode of it. You can have code, graphics, text, and interactive elements all within this same document. This is exceptionally useful when researching and working on solving complex questions that you find in computational thinking type activities. As I've mentioned before, bringing in and working with real-world information and data is critical. One of the really nice things about Wolfram Language is that there is so much readily available built-in knowledge in the language itself. We fully merged the data and natural language processing capabilities of Wolfram Alpha and made them available programmatically through the Wolfram language. So here's an example. I typed in natural English, countries in South America. Now I've brought in what we call an entity class of information. I can make queries on this entity. What is the flag for each one of the South American countries? Or perhaps instead of the flag, what is the name and population of each one of the countries in South America? Again, this information is built into the language itself. Now that we've had an overview of what computational thinking is, the tools to use to support it, I wanted to give a few example activities that I feel elaborate the characteristics of computational thinking activities. Came up with a couple of messy questions. The first one being, how stressful are tests? It's interdisciplinary. It focuses on math, psychology, physiology, perhaps biology and chemistry. You're asking the students to clearly define, what does this question mean? What are the sub-questions that go along with this? Perhaps a possible strategy for trying to answer this question is to choose a wide variety of students, run some experiments, collect the data, how stressful were they, determine the physical effects. Now again, we talked about bringing in real-world data. We can deal with messy type problems. We can deal with messy data. We can deal with lots of data. So here's something that's really nice is that I've brought in information of a heart rate monitor, and I've animated it in Mathematica with the Wolfram language. So this is something that you can easily bring into the problem-solving process. Continuing the activity further, ask and collect more data. Ask more questions. Ask refining questions. Does the study reduce stress in all cases? Does extra sleep reduce stress? Are there particular subject areas that cause more stress than others? So again, it's challenging students to think like a developer, to think like a computer scientist. What are the problems? How do you address it? How do you analyze it? And then go back and perhaps do it again. Here's my second question. And one of the reasons why I like this one is because you're bringing in computational thinking into a subject area like English or language arts that historically has no presence in those subject areas. So my question is, how well do I write? Well, obviously you'd have to work with the students to define that question further. Well, what does it mean to write well? What are the things that we're looking for? Once you define the question, you would take samples to determine a rubric. These essays over here define a well-written essay. These over here do not. Explore the data. Determine an algorithm to automatically take a first stab at determining how well-written an essay is. And there's ways to do that programmatically as well. Here I'm bringing in a sample essay from the ACT website. So let's take a look at how many words are in that essay. Perhaps that's one of my characteristics. Does the number of words make the essay well written? Okay, so let's take a look at the individual words. Perhaps it's not how many words there are, but the frequency in which certain words appear. So I'm going to go ahead and tally my words. I'm going to do this so it's nice and sorted. And now it goes from least frequent to most frequent. I'm going to go ahead and reverse that. So we can get a brief glimpse of what words I've used or what words are used most in the sample essay. But that isn't very compelling. Let's go ahead and make a bar chart of these. The data is visualized much better. Let me scroll down a little bit. Here you can clearly see that the word you is used most frequently by far, and then it gets down into to, that, school, etc. Perhaps that adds insight into how well written this essay is. Perhaps word length plays a part of how well written an essay is as well. Let's take a look at the average. So an average word length in this essay is about 4 words long. So let's go ahead and take a look at how long my words are. Again, not very compelling. It's a little difficult to see any trends. So let's go ahead and put this into a bar chart. So you can see from my bar chart here that I have a lot of very small words. I have a lot of 2-letter words, 3-letter words, 4-letter words. This visualization adds more insight into how well written my essay is, depending on what my students define as well written. Continue the process of thinking computationally about this problem. Does the length of the essay make it good? What about word frequency? What about individual word length? And there's so much more. But this adds a little bit of insight in how you would bring computational thinking and programming into a subject area like English or language arts that normally they are 2 separate courses. My next question is, how does a natural disaster affect the economy? Again, a messy question. There are so many aspects and facets that you're requiring your students to focus in and clearly define what does it mean to affect the economy. How do you determine it? Again, the process could be something like define the question. Focus on one or a few natural disasters, explore the data, and determine a correlation if possible. There are a variety of ways to support this with programming capabilities, but here's one. Financial data is available in the Wolfram language. You can pull in lots of information. Here I'm pulling in the financial data for Microsoft and Apple from February 15th to February 25th of 2015. Next, I'm going to plot the two next to each other. We're talking about natural disasters, so let's bring in some information about a specific natural disaster here in the U.S. Hurricane Katrina. Okay, so we have our tropical storm. Let's go ahead and find the start date. And then the end date. And then we can use that information up here in the financial data visualization. We'll need to take a look at the dates around August 23rd through August 31st, 2005. Again, these messy questions lend to other questions to clearly define the problem. Again, there are additional questions that need to be asked in order to define the problem. What companies would be affected? What is the best way to display the data? Does the correlation hold true for other natural disasters? So these are things to just get started thinking about what might a computational thinking activity look like or entail. My next question is, how do you identify a poisonous plant? Again, the definition of the problem, the definition of the question is essential when dealing with these messy questions. Focus on a few plants. Challenge your students to define an algorithm or series of steps for correct identification. Then automate the process. How can you use computers, the Wolfram Language, to handle that algorithm automatically? This particular problem is dealing with machine learning. There are already some built-in machine learning capabilities in the Wolfram Language, which has image identify that makes its best guess on what this image is. For instance, it made a best guess that this is a maple. But students can develop their own machine learning algorithms. Here I have a very, very small training set. You'd want it much larger, and this would be part of the project that the students do. But here you can see that I have a couple of different leaves and their associations. So this image, this image is shown as poison ivy. This is another poison ivy. This is a poison oak. Have some more poison ivy, and these images are birch leaves. I'm going to go ahead and assign that to my training set. We have a built-in function called classify, which is part of that machine learning, that training aspect. And now I can go in and ask it to try and classify what this image is based on my training set. Now I can ask my poisonous classifier function to see whether or not, or its best guess about what this leaf is. And the best guess is poison ivy. Again, this is one aspect of trying to answer this question, is how do you identify a poisonous plant? This is just one aspect of it. With computational thinking activities, it's multifaceted. Once you define the question, inevitably there will be additional questions to try and answer. But with the Wolfram Language, you can support answering, trying to tackle these messy questions. We understand how challenging it's going to be for educators to not only bring in a new way of approaching problems with computational thinking, but there is an additional challenge of getting students to program when perhaps they have never written a line of code before in their lives. We're developing the Wolfram Programming Lab to address that specific issue. In addition to being a very non-threatening programming environment, we've created a series of computational thinking activities called explorations. And here in a moment, I'm going to go through a couple of them. These explorations should be used to introduce programming, highlight possible applications and functionality. These explorations could also be the hook activity for larger computational thinking projects or units. In addition to the individual activities called explorations, the Wolfram Programming Lab offers the unique capabilities of being available online and offline for programming. Another feature of the Wolfram Programming Lab is that you'll be able to deploy interactive apps and web forms. Here's an exploration called picture patterns. We're going to be making patterns by repeatedly reflecting pictures. It's a nice interface. We tried to keep the text as short as possible, knowing full well that students sort of skim through what's written. We've tried to outline the bare basics, the bare bones of how to address this issue. We've included all of the text. We've included all of the code to avoid any possible syntax issues. We wanted students to feel comfortable and successful the first time that they interact, quite possibly the first time they interact with a text-based language. We also have some nice user interface features. For instance, if you completely mess up this line of code, you can restore the input. If you'd like to know more about what's happening in the code you see here, we have these show hide details, which elaborates and explains sort of the inner workings of the function. I'm going to go through this one pretty quickly. So again, here are my directions. Get a picture of something. Give it the name pick. So we can use a picture of a bird. I like picture of Darth Vader. The next step says reflect the picture top to bottom. Try other reflections like left to right. So I'm going to go ahead and try this first. But now I can try other things like left to bottom or left to right. Again, if I mess up majorly, I can restore the input so that I know I can get back to the original code. Join the picture in its reflection. Next step is to reflect again vertically. Code getting a little bit more complicated. It says repeat 2 times, try more times. I don't know if you can see it, that the 2 is highlighted a little bit, so I can adjust that. So let's try 5 times. Whoa. How about just 3 times? Resize the picture to keep it from getting too large. Try other sizes besides 400. So I can try 200. Okay, that makes it smaller. Try 800. That makes it larger. And there we have it. The student was introduced to some specific functions, programming syntax, all the while doing something engaging and interesting. Here's an interesting exploration that utilizes Twitter. It's called hypnotic tweets. You're going to make a program that draws hypnotic patterns and tweet them to our Tweeter program. The Tweeter program is where if you use the Wolfram Tweeter program handle and you send Wolfram Language, that'll actually execute it and return the results to you. So my first step is to run the code to default to create a rectangle. I could try other things. Oh, okay, triangle, great. Draw a stack of black and white squares. Try numbers other than 20. So again, the code is all there, but it gives me things to try. So I become comfortable editing and working with a programming language. Add rotation. Try other amounts of rotation other than 2. Make the number of squares interactive. If you're unfamiliar with the Wolfram language, this function here called manipulate is very powerful to create a nice GUI interface without actually having to code the user interface with the slider, how it looks, and things like that. Again, add a control for the amount of rotation. So now I can play around with two things. The next step is to show the values of the controls. Find values that make an interesting design. So I'm going to go ahead and evaluate, and here I have different values for N and for A. Ooh, I kind of like that one. So N is 53, A is 15. So it just allows the student to interact with it to make their own design. My next and final step is to send the program for your design to tweet a program. And you can try other designs as well. Inside the show hide details, it lists out where you should place the various values of A and N, and then also a step-by-step walkthrough about how to connect to Twitter through the Wolfram language and the steps to tweet your program to tweet a program. Okay, I'm going to connect to Twitter. Okay, I've been connected. I'm going to go ahead and send out my tweet. I'm going to switch some values here. So I chose 53 for N. And then for A, I chose 15. Okay. So there I've sent off my tweet to the Wolfram Tweeter program. Let's go ahead and check. So you can see here the Tweeter program bot sent back my computed results in Twitter. I can go ahead and retweet that. And there we have it, how to send tweets from the Wolfram language and to post them on Twitter. The last exploration that I'm going to highlight is called Words Near Your Name. Find words that differ from your name by the fewest characters. So again, introducing various programming functions to students, making them feel comfortable, and avoiding syntax errors whenever possible. Dictionary lookup returns a list of dictionary words. Edit distance computes how many characters have to be edited to get from one word to the next. So the difference between rhino and rhino is 1. So let's try other words. So test and retest. 2. Find words that differ by less than 3 edits from Sophia. We're selecting from the list of dictionary words, words that are less than 3 letters different than Sophia. So we have a list of words that here are 3 less than Sophia. So if we do my name, here are the words less than 3 that differ from my name. Find collections of words that differ by edit distances up to 3 from Sophia. Try other names and words. So here is the difference of 1, here's the difference of 2, and here's the difference of up to 3. 1, 2, and 3. Like I said, these explorations in the Wolfram Programming Lab are introducing a programming language that they may or may not be familiar with. It gets them working with the code, gets them familiar by seeing the square brackets. They begin to understand and to realize that all functions are capitalized. We see that there are different things like this slot syntax. What does it mean? You can go in here into the Show Hide Details to learn a little bit more. We've gone through a lot today. We talked about computational thinking, what it is, what computational thinking activities look like, the tools that can support bringing in computational thinking into the classroom, some sample activities and how the Wolfram language can support them. I wanted to list off briefly, I know that I jumped through some code and some resources that you may or may not be familiar with, so I've listed them off here. We put together a page for the Hour of Code, which has resources on it. We also have the Wolfram Language Code Gallery, which highlights mini programs that you can do in the Wolfram language. We also have the Wolfram Demonstrations Project, which is an online database of over 10,000 interactive knowledge applets. You can take a look at the code, edit them, and use them in your classroom. If you'd like to continue your learning with the Wolfram language, we have a website strictly dedicated to learning with free on-demand courses and scheduled training sessions. That concludes our workshop. I challenge you to explore computational thinking activities on your own and see if you can incorporate them into your own classroom. Thanks again for attending.